So as we're getting set up for this lecture, you can look in the box. There should be two new SLA lectures. One is SLA 8 and one is SLA 8.1 showing some examples. So we're going to start stereolithography and photopolymerization as soon as my PowerPoint starts to work here. So you can download those and follow along. And if the internet's not going to cooperate, we'll make another plan. Hold on one sec, bear with me. Okay, got YouTube set up. Give this one more try, left box sync up here. Okay, as the slides start coming up, I'll start talking. Hopefully, Box will make it happen here in a second. But you should have all seen that Canvas discussion link, and let me show you on Canvas. Well, I can't get on Canvas either. But anyway, there was a really nice explanation of SLA chemistry that was uploaded as a link on the discussion. And we're going to talk about that. And we're going to talk about SLA printers as we start this new unit on photopolymerization, stereolithography, the different modes of stereolithography, and how photopolymerization 3D printing compares to the thermal type of shaping that we've seen thus far. Now, remember in convex printing, oh, something's going wrong here. Let me just try this one more time. Now, in convex printing or in PolyJet, they also use photopolymerizable inks. So we talked a little bit about liquid inks last time or the lecture before. And so it's very similar chemistry. So we're mostly going to talk about UV photopolymerization of acrylates. And that's exactly the type of chemistry that PolyJet uses, is this UV photopolymerization. And you can tell because they use a blue light, which tends to signify UV light. Of course, if it's too short wavelength, you won't be able to see it. So you can't see 250 nanometer light, but oftentimes they mix it with a little bit longer wavelength or have a blue LED there too. So you know the light is on, because UV light can be dangerous. It'll give you sunburn, it'll give you, it'll burn your corneas, other things like that. But UV in general is going to be wavelengths, there we go, wavelengths between 200 nanometers and about 600 nanometers or so. That's going to be our span of UV wavelengths that we're going to use for this stereolithography photopolymerization. So before we get started here, now that we have slides and everything seems to be working, are there any questions from last lecture or questions on SLA in general before we kick it off here?
Do you know when you're going to post homework for the last unit, I guess?
Oh, yeah, sorry, I'm one cycle behind on homework, so I'm gonna try and post that probably tomorrow, but I'll give you a week and a half as usual. And the next homework, just to give you a preview, will be on unique printing processes. So you'll be able to pick a process, you'll be able to study it, and we'll talk about you'll be able to pick papers that you're interested in, and then we'll start to talk about final project and what your final projects look like, because it never hurts to start planning that. They'll be due in 2 months, and so I'll get back on track with assignments, but there are no surprises in terms of what the assignments are going to be. They'll be straightforward. Read papers like we've done before, think about them, and then talk about what you're interested in. But I'll get on that. Thanks for the reminder.
Thank you.
I kind of have maybe a random question, mostly just like curiosity, I guess.
Sure.
When you're using like polyjet or inkjet and you're basically like using a liquid base, do you ever have like issues with like cleaning, or like is that pretty straightforward? Like, do you often like, I don't know, I'm just worried, like, would you get like contamination when you're like moving from one product, like one part to the next, if you're like switching materials?
Oh, all the time. So anyone who's worked on a binder jet system or an inkjet system or even SLA, I mean, I brought up this diagram here because there's a couple different places where we use polymer liquids. And if you've ever dealt with solvents or with Elmer's glue, or not quite super glue because it doesn't harden that much, or epoxies, cleaning those things is impossible. And so that's why when you buy an inkjet cartridge from HP, the inkjet head is part of a new cartridge. And so if you've ever tried to get one of those kits to refill an inkjet printer cartridge, it doesn't work very well because the heads wear out, they get clogged. If anyone's ever used an X1 binder jet system, those heads get clogged. Now, HP has come up with some cleaning routines. They use special solvents in the inks to prevent clogging, but yeah, contamination, clogging, heads not working, all of those things are hard to deal with. And it really gets down to the nuts and bolts of the printer and what solvents they use in the ink and what ink formulations they use to try and keep the printer working the way it should. But yeah, it's a major headache to clean all of these types of printers, including SLA. So if you've ever worked in an SLA printer, these are viscous resins. They're really hard to clean. So contamination and cleaning is a major issue.
All right, thank you.
Yeah, and if anyone's ever worked with like a lab scale inkjet, they're really hard to keep going because lab scale inkjets, you can clean them, you can do all sorts of stuff, but you tend to have a big budget for buying new inkjet heads because they're really hard to keep working all the time, especially when you're using experimental materials. That's a good question. Any other questions or any other discussion points? Okay, so we're, in general, I'm going to refer to this as SLA, and SLA is short for stereolithography apparatus, as we'll talk about in a second. But where we're at on the ASTM diagram is, of course, we're talking about polymers. We're going to talk about chemical reactions, and pretty much we're only going to talk about photochemical or photopolymerization. We're going to talk about liquids, and we talked a little bit about liquids before in terms of high-speed sintering and binder jetting, but now we're going to live in terms, and we've talked about material jetting as well, where we're putting this liquid material through a print head, but mostly we're going to focus on that photopolymerization. And so this is SLA, or sometimes it's called DLP, or Carbon calls it CLIP. Azul calls it HARP. If you know who Azul is, the next 3D printing company that's faster than Carbon. And so there's lots of different terms for this, lots of different acronyms. There's actually lots of different setups as to what the light source is, how you pattern the light, whether it's a top-down illumination or a bottom-up illumination. We'll talk about all those things, but this idea of vat photopolymerization, where you have a tank or a vat, and then you're doing photopolymerization or light-induced polymerization in some way is what we're going to be talking about. And of course, this is different than what we've previously discussed with light. Remember that SLS is also a laser-driven process, but this is thermal. And generally, you're going to use a long wavelength light source. So you're going to use an IR laser or IR lamp in the case of jet fusion or high-speed sintering. And so those wavelengths are on the order, lambda is on the order of 2 to 10 microns or something like that. And so in this SLS, remember we have a powder bed and we're going to fuse powder. That's why this is called powder bed fusion. And so SLA is going to look like this in some cases, but there's really different stuff going on in terms of the polymer chemistry and the physics of the process. And also, you don't necessarily immerse your part in a powder bed that can act like a support. It's still immersed in liquid. And of course, liquids are not going to be very good supports. And so even though some of the diagrams look the same, what's happening in the embodiment of the instruments are quite different. And so we're going to be fully switching gears here in all respect. So photopolymerization, or this chemical reaction bonding, happens in UV light or sometimes in visible, but it doesn't happen with IR because there isn't a lot of IR-induced photochemistry. And so we're going to be causing specific chemical reactions with light. And so that's under the banner of photochemical reactions. And this is not a polymer chemistry class. If you want to know more about all the different polymer chemistry that we're interested in, we can talk about that, or you can study that. And we'll cover it a little bit in terms of acrylates, but we won't go too deep into all the different organic chemistry because I don't think that's everyone's interest here. So this is a diagram worth knowing. And Chuck Hull, who started 3D Systems, is still alive and still is the Chief Technology Officer of 3D Systems. He's one of the heroes of additive manufacturing, and this is the patent for stereolithography apparatus. Now, back in the 70s and 80s, if you were in an engineering department or if you worked in an engineering research group, oftentimes this would be called rapid prototyping. And they called it rapid prototyping because it made very fragile models. And the models were fragile because materials were not robust in terms of engineering properties. So as we get into this unit, we're going to talk a lot about elastomers. We're going to talk about tough materials. We're going to talk about ceramic resins. Really, the innovation in SLA or vat photopolymerization is really in the materials. They've been able to do this process since 1986 or even a little bit sooner with some other types of processes, but the materials were not up to speed. Now we have engineering materials, we have post-processing, of course we have great computer control and other things like that, but the real innovation in vat photopolymerization in the last 10 years has been in the materials. So we're going to cover a lot of general stuff in the first lecture or two, and then we're going to talk in detail about all the different materials that can be achieved using this process. Are there any questions so far? Any comments? Okay, I think I had the chat up here. So if you want to interrupt, you can unmute yourself. Otherwise, you can just type your questions into the chat, and hopefully I'll catch them. So there's a couple of key parts about this process that we should pay attention to. So we have a vat of uncured liquid resin. In this top down, because we're illuminating from the top, the resin is recoated over the surface of the part with this recoater right here, and there's usually a reservoir next to it, like a powder bed recoating. You have a build platform that moves down into the vat. And then the laser and optics, all the lenses and other things aren't shown right here, but this is UV wavelength, and we'll talk about specific wavelengths and what are chosen in a second. Lambda equals UV. And this is a galvanometer point scanning system. So a galvanometer is what moves that mirror, that moves a laser. And so each voxel in this part, or each area that you want to change from liquid to solid using UV photopolymerization, the galvanometer has to trace that area out. And we call this point scanning. Are folks still there? Yeah? Hold on, it said transmission.
Yeah, we're here.
Okay, it said transmission stopped, so I don't know what happened. Let me try and broadcast again. Hold on one sec. Always some new Zoom adventure. Okay, it looks like we're still recording, and it looks like I'm broadcasting if my other computer's not lying to me. So let's see what happens here. Like I said, the internet, at least at my house, is not feeling well today. So anyway, this starts to set us up for what these different geometries of SLA look like, what's going on, and why this is so different than what we've studied before. So we're not going to talk a lot about TG. We're not going to talk a lot about TM. We're going to be talking about extent of cure. We're going to be talking about different photo initiators. We're going to be talking about different wavelengths of light and how to steer that. So we do have to switch gears a little bit here. And this is just a little bit different look at some diagrams that you'll see in the literature. And so you can check out this paper right here. But this again would be top-down raster scanning or laser point scanning system that basically writes one voxel at a time, and the part sinks down into the vat. This DLP projection system, this projects an entire 2D layer, so entire with one exposure. And that exposure can be longer than the dwell time for the raster system. It'll be on the order of 100 milliseconds or 10 milliseconds. It honestly depends on how bright the lamp is and the type of photopolymerization that you're trying to do. This DMD is called a digital mirror device. This is what's in old DLP TVs. It's actually what's in LCD computer projectors right now. And so this DMD is the engine that makes the pattern for whatever sort of shape we want in our layer. So rather than scanning a point at a time with a galvanometer and a point source laser, the DMD basically floods a patterned image. You can think of it as a black and white projection of whatever pattern of interest there is. And we'll see examples of both those things as we watch a couple videos to get us oriented to what's going on here. So I've got some YouTube links. We're going to watch the first one about photochemistry. We're not going to watch the whole half an hour, but we're going to start with just a little intro from the link on Canvas. And let me, screen broadcasting has stopped. Let me get it back. Okay, we'll see if we watch any videos today. Okay, well, we'll see if this works. If not, you can watch the videos as homework. But we'll give this a try, and we'll watch a couple minutes of the first one just to see how it's going here. Like this is, yep, this is the right video. All right.
I've been obsessed with belts for a long time. I wear a belt every day, and there was like 3 things that
Right.
always drove me crazy about belts.
And
Okay, here we go.
welcome to Goobertown Hobbies. My name is Brent, and I love to print and paint resin models. So today I'm going to talk a little bit about how 3D printers work, but I'm going to talk a lot about how resin works. These printers turn liquid resin into solid plastic figures. They print one layer at a time. A motor moves the build plate above an LCD screen and a vat of resin. The resin vat has a clear bottom. UV light from the LCD screen goes through the bottom of the vat and polymerizes a layer of resin on the other side. The screens have a resolution similar to a modern cell phone, so the polymerization is precise and the models come out with really nice detail. Part of what makes these printers so cool is how simple they are. Just one linear actuator and one LCD screen, and that's about it.
So they are relatively simple. And so the linear actuator is the up and down movement. And what we've been seeing so far is sped up. These printers are pretty slow, like 1.5 seconds or 2 seconds a layer. And it's not an LCD screen, and it's not like a cell phone screen. It's a DLP projection system. And we won't talk necessarily about all the different electronics and optics that go into that. But you can look into, if you're interested in the mechatronics or the electrical, mechanical engineering of printers, there's a lot of homemade printers out there. People have studied this, but if you buy a DMD from Hitachi or Texas Instruments, you're basically shining a high intensity light on that micro mirror, and that's projected up through the clear window that we saw in the previous slide. So it's not like a screen, it's an actual projection system, more like a computer projector. So let's keep going just another minute or two here.
Screen, and that's about it. So the technology that's in these bottles is just as amazing. You hit them with a little bit of UV light and they harden up just where you want them to, and they stay liquid everywhere else. So how does that work? Okay, the building blocks of polymers are monomers. These are small molecules that have the potential to form chemical chains. Just like building blocks, they have structural features that allow them to connect. If we initiate polymerization, the monomers will start to link up to form dimers and trimers and tetramers and beyond. These short chains are called oligomers. Once the chains get longer, they're called polymers. A single chain can contain hundreds or even thousands of monomer subunits. Nearby chains get tangled with each other, and by now the whole thing is normally a solid. The properties of a solid depend on things like what monomer you started with and what the average chain length is. Something else to know about polymers is that they can contain multiple ingredients. Most of these liquid resins use a proprietary blend of different chemicals. Us folks who 3D print as a hobby are always comparing notes about different resins. You know, which ones are hard or soft or brittle or hold detail really well. And in broad strokes, it's the same thing going on in all these bottles. It's all acrylate chemistry, acrylate polymerization, but in the details, there are actually a lot of differences between these different blends, and that's what we're going to talk about. It is perfectly reasonable.
Okay, well, that is very interesting. And of course, I could watch the whole thing, but so can you in your own time. Very soothing podcasting voice. So that's nice. But there were some key parts of that. And so in general, and we'll talk about the key parts and break them down in coming lecture, but what we're interested in is this liquid to solid transition. Of course, there's really unique 3D printing processes out there that make semi-liquids or liquid-filled robotics or something like that. But the basic idea is that the laser induces a liquid to solid transition by building up from the monomer to a ligamer to polymer. And so this photochemical reaction causes, or this chemical reaction bonding basically causes an increase in molecular weight. And in general, if we have the right chemistry, when we increase molecular weight from monomers and oligomers to polymers, we get this liquid to solid transition. And that can happen extremely quickly, within 10 or even 50 milliseconds. And so the photochemistry is extremely fast, and it's all the other movement of the printer and movement of the stage that slows the process down. So we'll talk more about photochemistry as we go on. Are there any questions so far? Okay, so we'll look at a couple of other videos just to continue to get the physicality of this. And we won't necessarily focus on the chemistry too much. However, if you're interested in the chemistry, you can look into it. And of course, people are going to have to bear with a little bit of chemistry right here. And it's instructive to know the basics of the chemistry so you can troubleshoot problems in the future. So we're going to look at a couple of other industrial printers and get an idea of what this SLA process is all about from a couple different angles. So let's see if this one works. Well, Zoom is certainly not feeling well, but I'll give it one more try here. And this might be the last video of today. All right, let me give this a go. And this is linked in the slides, so you can always check it out. So this is interesting because they're going to use 3D Systems Viper Pro SLA. So this is top-down raster scanning, exactly like Chuck Hall patented.
Hello, my name is John Harward from Tangible Express, and we want to show you a little bit about our company, what we're about, and some of our machines. So why don't you follow me and we'll check out some Viper Pros. We got to do this handy dandy finger scan first. Let's go check out where the magic happens. As you can see, we've got
Okay, so first you notice these are not little desktop printers anymore. These are not hobbyist printers. These are big machines. So this is double size refrigerator, and you'll see some big parts printed on these if you watch the video links as we go forward. So they're printing big stuff on here to start with.
7 Viper Pros back here, dual rack. What is so cool about our stereolithography machines is this is the latest and greatest Cadillac machines in the industry. Right now, as you see, it is doing borders and fill rates. It's a stereolithography machine. That laser is moving at 1,000 inches per second. In this vat, we have the Acura 60 by 3D Systems, one of the most popular for the stereolithography, mimicking or giving you a polycarbonate-like process. After this Viper Pro, Acura 60, and Acura 25. So you have the Acura 25, Acura 25, followed by the Acura 60, Acura 60.
He's talking about the different resins.
The no-name bluestone. Acura 60. Followed by more Acura 60. The Acura 25. And Acura 25. Now, do you want to show them our fancy screensavers?
Okay, let's see. This one shows some parts. So let's just take a look at this and then we'll move on if this is going to work here. This one's a little bit of an advertising video from 3D Systems, but it shows some nice parts and the recoding and printing. Okay, so that's all very interesting, and you can check out the rest of those videos when you have time. But this starts to get us into a new mode of additive manufacturing with advantages and disadvantages of its own. And so we can compare and contrast these processes to the other processes that we're interested in. And one of the important parts of what we're going to talk about in SLA is that the general class of materials that we're going to use are thermosets, not thermoplastics. And so when we talked about powder bed fusion, or certainly when we talked about material extrusion AM, we were using polymers that were already synthesized, already purified and ready to go, and they were thermoplastic. And in general, they could just be formed by heat, and they could be shaped by heat, recycled, melted down, used again, made into new pellets, etc. Thermosets, even though they're called thermosets, maybe we can call these photosets because they're not thermally polymerized in general, they're photopolymerized, but thermosets and photosets are the same class of polymers in general. Thermosetting polymers that can't easily be melted, they can't be reformed. Now they can be ground up, but they're not reactive once they're ground up. And so they're basically just dead polymer powder that can be used as filler or something else. And so there's different things going on with these thermosetting polymers versus the thermoplastic polymers that we've discussed before. Also, because they're reactive chemicals, you just can't put them in a bag. You know, you can't hold these polymer pellets in your hand. The polyethylene is generally pretty non-toxic, other than the dust, of course. But these are reactive chemicals, and so these are a lot more like organic chemistry things that have their own set of hazards rather than melting plastic that isn't too bad as long as you don't get it too hot and start smelling all the styrene coming off of ABS or something like that. So my suggestion is to, if you're not familiar with stereolithography and these types of processes, watch some videos, sort of think about how this process works, and we'll dive into the details as we go along in the next couple lectures. Any questions or anything that people want to bring up while we pause here for a second? All right.
I have a quick question. Sorry for the delay.
No problem.
When you're
Go ahead.
dealing with when you're working with machines like the ones from this last video where the laser comes down from the top versus from the bottom, are there any viscosity restraints in terms, because I'm assuming that there's going to be a fixed layer height where you have the part under, for all intents and purposes, underwater or under resin. So if the viscosity is really high, would you have any surface tension or problems in regulating that?
So,
You know what I mean?
yeah. So viscosity and surface tension are different, right? And so in terms of surface tension, organic liquids tend to be good at wetting other things, especially wetting polymers. So if you look at the contact angle of toluene, which is an organic liquid, it's always a lot lower than the contact angle for water, because water is a high surface tension liquid because of its unique structure. But polymers tend to be good at wetting, and the viscosity is tuned for the specific process and also for the speed of the process, because viscosity is going to be resistance to flow. And so
Sure.
in some cases, like if you're doing say a bottom up DLP stereolithography where you try and get resin into this gap, so you'll see a lot of printers like this have a wiper, or they move the build tray a little bit in order to release the suction right at the interface of the window and the part. That's due in part to the higher viscosity of this polymer bath in order to break that suction. So you tend to need low viscosity for bottom up DLP, and you can get at higher viscosities with this top down. So you still need to have reasonable viscosities, like honey is a maximum viscosity for a lot of these resins, but the viscosity is tuned to the process. And we'll talk about how to adjust the viscosity of SLA resins. You can add what are called reactive diluents, which are basically solvents that are monomers. So the solvent, or the thing that lowers the viscosity, actually becomes part of the polymer chain, because you just can't add solvent to this. These are solvent-free processes. But you know, I think there's a range of viscosities that you can work within, but definitely for top down, you can use higher viscosities than you can for bottom up because of the part release issue from the window.
Well, and that's 100% true. But the advantage of having, actually, this is a perfect image. So the reaction window and the black air there that you have, that's going to be a fixed distance. So your layer height is always going to be 50 microns or 100 microns or whatever you want. It's going to be dead on the entire time. So I guess from a layer height standpoint, does the slide 7 image have any, is that going to vary layer height, or is it still going to be regulated or able to be regulated to the same degree as slide 9?
Yeah.
Like, is it going to be a dead on 50 microns every time? Has it been 100% calibrated, or is a high viscosity or high surface tension liquid going to have cupping on the top of the part?
So that's a very good question, because the gist of Eric's question is, this is a free surface. So let's go back to the bottom up.
Exactly. Thank you.
This is a trapped polymer layer between basically two solids. Now the windows tend to be a little bit flexible, but not that flexible. But this is a controlled layer height because you're going to build a new layer right at this interface right here. In this, there's a free surface because this thing is filled with nitrogen or oxygen or something like that. And so what controls the layer height in this case is the distance between the wiper. So this is a wiper.
Okay.
And the solid part. You can't see the solid part because it's clear, but there's a solid part here, and the solid part is going to have a thin layer of resin right on the top. Now, what's interesting about these photopolymerized layers is that they're a little soft. And so you don't, even in this, we say that the polymerization is going to be between two hard objects, but companies like Carbon leverage what they call the dead zone at the window. So their gap is not necessarily the gap between the part and the window, it's the gap between the part and the dead zone. And at the edge of the light, the part is a little bit soft. So you have 5 or 10 microns of wiggle room. So even though your layer height might not perfectly be controlled here, the very top surface of the resin is not necessarily as hard as the rest of the part, and that's wiped through with new resin. And so this picture of layer by layer, these are not perfectly hard layers like we think about in material extrusion AM. They're a little bit diffuse and they're overlapping. We don't necessarily see these layer effects in the same way. But if you have the same viscosity and you have the same tolerance between the part and the wiper, you will get the same layer height every single time, even with a free surface compared to a bottom-up gapped process. And so as long as the viscosity and surface tension don't change, the resolution of this process is exactly the same as the resolution of this process. It's just if you start to get old resin or if you start to get aging of the resin as you're building, that can cause problems in both of these. Even we could talk about getting bad filling in here. Prints fail sometimes if the viscosity is too high and you don't get a fully filled gap, which can happen. Same thing can happen here, but usually the process is consistent enough, and as long as the viscosity is consistent enough, you'll get precise layer height with top down.
Very cool. Okay, thank you.
Yeah, but that layer height, as you change viscosity, so say you change resins, now you're changing the viscosity, you can have, you need to dial back in your layer height, because the layer height is not necessarily always the same as the gap between the solid part and the wiper, because you do have a little flow in here. But that's generally taken care of because this interface, the very top of this resin, stays at exactly the same place because of this wiper, and then the part moves down. And so the gap is really defined again by the distance between the wiper and where the build platform is. The gap is really not controlled by the fluid dynamics of this vat.
Okay, but from what I think you said at the beginning is the minimum layer height of a liquid can change from liquid to liquid if your viscosity has large ranges. Like one liquid may have a super low viscosity and can get away with 50 microns, but something that's a lot higher, like 6,000 or 7,000 centipoise, might not be able to do 50 microns with this specific type of.
I mean, I think that's certainly possible, but that might that's also an issue with this, is that for a high viscosity resin, you just can't flow it in to the gap. And so as you go down to these really small layer heights, you probably need resins that are less viscous, and that might go for resolution as well. So there really isn't good data on viscosity versus resolution, but there's a lot of anecdotal evidence on this is a good viscosity range for this printer for this type of part. I think it's work that hasn't been done so far, because people have generally focused on photo initiator concentration, light reabsorbers, inhibitors, other things to get the resolution they want, and they just formulate the viscosity so it's printable. There's really no
really thing on material strength or any need to go really high. Because what in my previous job before I came here, when we were speaking with the Carbon reps, they said their general saying was, because we asked this, it was like, is there a viscosity limit? And their saying was, in theory, we could print peanut butter if we really need to. So they can
Well-
get really, now there's some type of like, they need to bounce their platform in the Z direction to really like creep that liquid in. But I mean, we never got that high. There was no reason to go that high. But it was,
Yeah.
because in other systems, viscosity is a very, very large limiting factor.
Yeah, I think that's right. That in theory, you could print really, really viscous materials. And some of these ceramic resins that companies are coming out with now are pretty viscous, but in practice, in order to get the prints you want, and in order to get the resin working with the machine that you have, you know, they couldn't print peanut butter in the machine that exists today. They would have to do some modifications. And so I think that's a completely accurate statement. And certainly the folks at Carbon know materials just as well as anyone else. But I think in practical printing with machines that exist, you know, we'll talk about ranges of viscosity and how to tune viscosity. And it really just depends on whatever process you're employing and ultimately what properties you want. Because the way to adjust the viscosity is you need to adjust the resin recipe. But if you have too much reactive diluent, you won't get the strengths that you want because you have too many monomers in there. And so we'll talk about those trade-offs as we go forward.
Okay, cool.
Great, good discussion. And if other people have had encounters with stereolithography or things that you've talked about with reps or other things you want to bring to the table, please let the class know. Just pipe in or put them in the chat, and we'd be happy to discuss them as we go forward. But that's really good input. Any other comments, questions? All right, let's keep going. So what this looks like, and this is a picture from my lab, is that you have your bottle of liquid resin. If people want to mute, that would be helpful. I think there's a little bit of background noise, so don't forget to mute yourself. Okay. There we go. I can mute people. Okay, so this is a liquid resin. So these are often called photopolymer resins or liquid resins or something like that, but this is a photopolymer. This is a DLP printer, so the light source is down in the bottom here and it shines up. This is the build plate. Build plate. This is the gap where the photopolymerization is going to happen. This is the vat right here where our part is going to be. And you see the patterned light coming up in this print. And Brandon's wearing his safety glasses because this is in my lab, so that's good. But anyway, this starts to give you an idea of what's going on. And so the only movement that you absolutely need is this linear actuator right here in order to move the part up so you can build the part here. So this thing moves up to form a new gap and a new layer. However, in order to release the suction between the part and the window, because of course this is liquid photopolymer, so there has to be a window at the bottom of this, you oftentimes see the plate being tipped or something else in order to release that suction. So you'll see build plates go up and down. That's generally releasing the suction and re-gapping the part. Sometimes you'll see trays tip. There's other things going on with the mechanical engineering of the printer, and we'll talk about that as needed. But as you watch the videos, this will get you oriented to what this looks like. We're not going to watch this video. I suggest you check it out. It's really awesome, but you can build one of these printers at home if you'd like to. And so what the parts start to look like is you can build these complex monolithic shapes, and you can build them relatively quickly. And so we haven't talked too much about build time or build volumes or some of the engineering of additive manufacturing. But you get that in other courses, or you can get that from the general information online. But you can see now these are complex parts, and they're generally single material. High resolution. Good surface finish. Finish. And they're difficult to print using other methods except PolyJet. PolyJet can produce these types of models. It can produce this types of complexity, but in a little bit different way, and you get a little bit different surface texture. But it's really hard to do stuff like this with material extrusion AM. Powder bed can make this type of part too, but you're going to have that powder surface finish, and so those parts look a little bit different. But SLA parts have these general characteristics, and the biggest drawback of this technique versus others is you're using these reactive chemicals, and you're generally confined to single materials, although there's lots of research innovation out there now looking at how do you do multi-material SLA. So when you see a 3D printed part, in general, you can identify at least the type of process that was used to make it. And so FDM, or material extrusion AM, is easy to identify because of the surface striations. And the industrial material extrusion AM just looks a little bit better. SLA and industrial SLA look the same. These are very smooth, and then SLS has the powdered type surface texture. So this is just a nice guide from Formlabs on how these parts look. And if you're interested in getting a sample part, you can get on Formlabs website and ask them nicely for one of these sample parts, and I think they still send them out free of charge. And so you can have a 3D printed part sitting on your desk if you want, or of course you can dial up a part from the Maker Commons at the Penn State Library and put your student fees to work. Okay. So it's easy to identify SLA parts when they look like this. So you can make pretty clear materials. Of course, if we're doing photopolymerization, clear is good, although they tend to, you can put fillers and colorants in them. If you want opaque parts, that's fine. But we haven't talked about clarity as something that's very easy to achieve in the material extrusion or SLS parts of the class. So you can do clear parts. These were printed upside down because they were printed using DLP from the bottom. That's cool. And you tend to have high resolution. Really between 25 to 100 microns. And if you remember, in SLS and material extrusion AM, the surface roughness of the parts and the resolution of the parts is on the order of 50 to 300 microns. And so you can easily see the surface finish and some of the resolution differences just by looking at the part. Then, of course, you can use optical profilometry or stylus profilometry or something else in order to get fine measurements of surface roughness. But we tend to get very good surface finish on SLA parts, and it's so good that some companies selling SLA technology, you can actually design in surface texture as part of your build. And so say you're into aftermarket car parts for car modifications, and some people like to see that carbon fiber weave in their dashboard insert or something like that. You can actually print in something that looks like a carbon fiber weave into a part when it's all just plastic. Or you can print in surface roughness if it's going to be a grippy part, or print in smoothness. And so that's a technology that SLA is able to sell because they can produce parts with such high resolution that now you can print surface features into the part to give the look and feel that you're interested in. SLA is also scalable, and there's some really big printers out there like this Pro X950. We won't watch the video, but this thing is big. This is a engine block or a plastic model of an engine block, and so you're not confined to just the small plastic toys and the demonstration parts, just like we have industrial material extrusion AM, and we've got relatively big powder beds and high-speed sintering beds. You can have pretty big SLA as well. It's a heck of a lot of photopolymer resin, but it's certainly possible, especially if you're committed to producing a showpiece like this, which is pretty cool. So that starts to form the basis of how we think about SLA and DLP technology. So we're going to talk about material properties, we're going to talk about photopolymerization, but I want to talk about some of the engineering aspects and about some of the key physics of the process as we get oriented to this technology, and again, compare it to what we know from the other printing types that we've studied. So are there any questions so far? Great. Well, as you're doing your YouTube studying, you can check out Carbon's video. It's pretty awesome. Their founder, Joe DeSimone, is a polymer chemist, and their VP of materials, Jason Rowland, studied as an undergraduate in my lab when I was at Virginia Tech, when I was a grad student. And Jason's a really good polymer chemist as well. And so the Carbon folks know a lot about materials, and they know a lot about polymers, which has been leveraged for their specific printing technology, which is called CLIP. And what CLIP is it's still the type of printing that we're talking about, where you have bottom-up DLP. So this is digital light projection with a DMD. And this imaging unit, as they call it, is a high-power UV lamp. Because, of course, computer projectors, when you have to replace the lamp in a computer projector, it's just a halogen bulb because you need all the different colors of the spectrum in order to do RGB color in a computer projector. And it uses the exact same DMD. The innovation that has occurred recently in some of these high-speed printers is the DMDs are UV hardened. And with a high intensity power UV lamp with an even illumination field, basically all you're doing is projecting an image in UV. And the image is ones and zeros, or it's black and white. And that's what does the photopolymerization patterning in this process. So Carbon's innovation is really in this idea of a dead zone, or of the inhibition of the photopolymerization right at this interface. And so UV photopolymerization of acrylates relies on free radicals. And oxygen so like oxygen from the air, O2 inhibits formation of free radicals. If you've ever tried to make a polymer by free radical polymerization and you don't have it sufficiently air-free, nothing will happen because the oxygen molecule quenches free radicals. And so what carbon does is that they use this oxygen permeable window. This is a piece of plastic, basically, that allows oxygen through and creates what they call a dead zone right at this gap where the photopolymerization happens. So this type of diagram, it's a little bit small in this figure right here, is exactly the same thing going on here, where the photopolymerization happens in this gap where the polymer bath resin leaks in between the part or the object that you want to print and the window. I guess the window is not labeled here, but let me just put window. And so Carbon's innovation was they didn't let the polymerization happen right at the window, because then you don't glue the part to the plastic window. You still have a little liquid in there, and so it's easier to break the surface tension of that liquid rather than to have to lift a polymerized part up off a glass window or a PDMS coated window or something like that. And so what this dead zone allows them to do is basically focus their polymerization right here off of the dead zone, still in a well-controlled layer, and they're able to do a continuous lift of their process, or at least a semi-continuous lift, while just flashing the lamp off and on. And in this demonstration, what they did was they sliced their object at different slices. So these slices of the object are the number of layers in the object. So slice 1, slice 2, slice 3, slice 4, etc. And this is really a demonstration of how they're able to write in surface texture depending on how it's sliced, and the coordination of this continuous elevation lift and the flashing of the lamp, because this thing still has to flash because this mirror has to turn off and on. It has to change patterns in order to build different slices. And so the UV lamp is flashing while this printer is undergoing continuous elevation. And so you can get to something that looks pretty darn smooth when you're flashing the lamp very quickly and have this continuous elevation. And that's how Carbon has been able to innovate in this space. The process is really interesting, and you'll see that the materials are really, really interesting once we get into it. Any questions on this? So this is a science paper that complements the TED Talk in the previous slide. So I suggest you check this out. It's really interesting. Joe is a really good science communicator. Granted, there's a little hype in there too, but that's fine because 3D printing is exciting, so it's okay to hype it. These folks really know what they're doing with materials, and so the process is cool, and the materials are really cool that we'll talk about as we go further. Here's what the dead zone looks like, and I think this is a video eventually, but well, maybe. Who knows if I can, I'd have to launch the slideshow. Anyway, you can see the video of the dead zone. It's on their website. Well, let me see if slideshow, see if this works. Okay, let's try this. There we go. So if you look carefully at this, and I'll start it again, the part is right here, and the part is going up, so that's the part being printed. So this is a solid. I think they put in some gold nanoparticles as fiduciary so they could see the flow of the resin. And so this is liquid resin filling the gap in the dead zone. And so they're getting polymerization right here that's not on the window. So this is the polymerization layer. Sorry for the red, but it at least it shows up. So you can see how this moves along. Let me try it again. There you go. And so in clip, this is not a perfectly well-defined layer. So even though we have, let me get out of the slide show here so I can look at my different slides. Great, that's cool. So even though we say, oh, it's a well-defined gap, or this is the exact gap as to where this polymerization occurs, you can see from the carbon video that it's a pretty well-defined gap, but this polymerization layer is not as well-defined as having a liquid that's confined between two hard surfaces. And that's okay, because when you turn off the light, the photopolymerization slows down greatly, but there's still a couple of living radicals around, and the part still polymerizes a little bit as it's moving up for the next layer. And so that's really interesting, because even though the photopolymerization mostly turns off when the light turns off because it's inhibited, and you'll see some of these resin recipes having inhibitors in them to make sure that happens and you don't get resolution bleed and other things like that, you still have this knitting together of the layers where the different layers are polymerized basically together because they're all made out of the same polymer. The reaction's happening quickly. And so you get some interlocking of the layers, not from melting together of the layers like in material extrusion AM or SLS, but the chemical interlocking of the photopolymerization that causes interlayer adhesion and less anisotropy layer to layer than you see from the other processes. Any questions on that? All right, so there's some nice papers out there from Carbon. There's some nice videos out there from other folks. And so as you start to get familiar with this process, you can ask about things that you have questions on, or if anyone has a favorite SLA video, feel free to post it on the discussion group. I had not seen the polymer chemistry one. That's very cool, especially with hobbyists talking about monomers to oligomers and polymers. That's great. So one of the things, or one of the advantages of this clip process is that you can get very smooth surface finishes. So this is on the order of 400 microns right here, where you don't see any layers. The layers are in there because the light has to turn off and on, so you get layering that way, versus a little bit different surface finish, or this scallop surface finish in a regular, so let's call this conventional, SLA. And the layers are actually adhered well to each other. So we have good interlayer adhesion in both examples, but this scalloping layer by layer occurs because of light bleed in the gap. So when you have this well-defined gap right here, you get a little bit of edge resolution issue right there, and that's where the layering comes from. So this scalloping, excuse me, this scalloping is caused by this little bit of light bleed when the light is on in between layers. So that's interesting. That's been studied. You can see it in the surface finish, but the interlayer adhesion is relatively reasonable. And so these are some of the parameters that we'll talk about as we go on and talk about what's going on with our SLA process, how do you control it, what's interesting. This is the dead zone plot right here and the inhibition of radicals by oxygen or air, because air is 21% oxygen or so. And so this shows inhibition of free radicals by oxygen. And of course, if you add more and more photons, so the photons create free radicals by photoinitiation. If you send more and more photons in, you get more and more photoinitiation events. And so the dead zone goes down because you're inhibiting less radicals. Or if you add more oxygen, you get a thicker dead zone because there's more oxygen around. The oxygen concentration is higher, sucking up some of those free radicals that are made by photoinitiation. So this is showing the trade-off between oxygen concentration and photon flux and how to create the dead zone of a certain thickness, which of course you can dial in, and from that you can dial in the speed, you can dial in the viscosity, etc., etc. And so they show some really interesting curves right here. And so they show millimeters per hour. So this is the speed of the lift, so up to 5 meters per hour. That's pretty cool. You could print a 5-meter tall part in 1 hour. And I'll tell you that Azul is doing this as well using a different strategy. They use a liquid window, or they use a liquid on top of their window. But this is very fast lift speeds compared to conventional SLA. You see the dead zone thickness right here. And then you see a combined parameter, which is just a measure of how many free radicals you're making due to the photon flux, photoinitiator, et cetera, et cetera. But that's just a lump parameter that's interesting. But this now is starting to really get into how do you engineer this type of process in order to get the part that you want. And it all relies on this UV activated acrylate photopolymer curing. So you'll see lots of terminology like curing. So that's just photopolymerization, or this is also known as cross-linking. Of course, lots of times we'll talk about a resin, and that starts off as a liquid. And then this thing right here, benzoyl peroxide, is a photoinitiator. It's not part of the polymer because it's not an acrylate, but this is the thing that absorbs light and makes a radical. And so if you want to make a polymer, you start off with initiation to make a free radical, and then that free radical propagates through these acrylates. And we'll pick up on this slide next time, but this starts to get into what are the materials, how are they used, how are we going to interface it with this SLA process. And so this will be it for today, but I'll open up the floor if there's any questions or comments that people have before we end it for today. Okay, well, we're moving into a new era here, so think about photopolymerization, think about what this SLA process is like, and we'll keep going over the next few lectures, going back and forth again between materials, process, and then what you can do with these different combinations of materials and additive manufacturing processes. So thank you very much. I will see you on Zoom on Thursday. Bye-bye.
Thanks.
Thank you.
See you. Thank you.